Welcome to ECE 302. This is lecture 5.10 on Gaussian whitening. I'm Professor Stanley. In the last two lectures, we introduced the idea of random vectors, and we also introduced the idea of high-dimensional Gaussians. If you recall the definition of high-dimensional Gaussian, the PDF of this high-dimensional Gaussian is given by this form. You have a covariance matrix sigma. You also have a mean vector mu. As I said previously, this high-dimensional Gaussian is completely characterized by the mean vector and also the covariance matrix. Now, in many practical data science problems, one typical question that we ask is, suppose I start with a Gaussian, high-dimensional Gaussian with zero mean and univariance, meaning that my mean is mu vector is 0, and also this covariance matrix is identity. Is it possible that I can turn these data into another Gaussian random variable, meaning that I have an arbitrary sigma, I have an arbitrary mu. Can I look at the random numbers that you have already generated? I do a transformation of these random numbers, and I want to turn it into a new set of Gaussian distributions. So that's the first question. The reverse direction is also very common. That is, I start with some kind of Gaussian distributions with some mean and some covariance. What kind of transformation that I should do in order to give me back the zero mean and univariance? So there are two directions, right? One is going from zero mean univariance, zero mean and univariance Gaussian to Gaussian of mean and sigma. The other one will be the reverse direction. You start with mu and sigma, you want to go back to zero mean and univariance. So this is a very important question, because what you will have would be a pair of random vectors x and y, and then what you want to do is to take a transformation going from here to there. You want to take a transformation f, and then going from here to there you want to take a transformation of g, so that when you define y equals to f of x, y will have the new distribution that as you want, and then you start with y, you take the transformation of g, you will get back the x that you want. So this lecture we want to look at these two distributions, these two transformations f and g, what they are and how can they perform these two tasks. So before we continue, we may ask, why do we want to study this problem? In practice, why do you encounter this problem? Well, in practice, you encounter this problem because you want to generate a noise to a specific form that you want. You may want to generate some kind of a pseudo noise pattern that you want to use it for testing some of your data. For example, you have a machine learning algorithm. You want to see how well it performs on some random data. And the random data has to be structured. It must have some kind of correlation structure. And so you ask, how do I do that? Well, you go from a zero mean univariance Gaussian, you turn it into another Gaussian. The reverse direction is also very common. For example, in communication, you have some signal that are received, and then they are corrupted by some kind of a noise. And this noise is not independent, they are not either Gaussian. So how would you handle those situations? You do a whitening. This process going backward from y to x is called whitening process. Usually this kind of noise is called a color noise. This kind of noise is called a white noise. It's white noise because the zero mean univariance is independent, is everywhere. So we call it the white noise. So when you go back from the color noise to white noise, it will become very useful because we know how to deal with white noise. However, dealing with color noise would be a lot harder. And so both directions you can have many applications. And so in this lecture, we want to understand more about how do we do these transformations. So here is the summary of the questions that we're going to ask. As I have said, we want to ask two questions. One is going from 0 and I to mu and sigma. The other one is going from mu, sigma to 0 and I. So these are the two questions that we want to address. So let me present you the first result, which is this question where you go from x to y. You go from 0 mean unit variance to mean mu and variance sigma. So the theorem is given by the following. You start with an x. X is 0 mean unit variance. So this is your random vector. For example, you can have a random vector x, which is two-dimensional. So x1, x2, this is your random vector. So you have 0 mean and variance being identity. That's your x. Okay, and let's say in your data set you have many of these x. And so for each one, so each of those, that is your x here. For each of those, you multiply it by the thing that you want. Okay, what do you want? Let's say you want to transform this x into a new random vector, which is y equals to y1 and y2. And then you know what you want. You want this covariance to be sigma. You want the mean to be mu. You multiply the sigma half and to x, and then you multiply. You add this mu to the product. So what it means is the following. You take this data point, and then this is your x, and then for every data point, you multiply this sigma 1/2, and then you add with the mu. Then the new distribution of your y will follow this. Okay, so the new distribution of y will be Gaussian with mean mu, and then the variance will be sigma. So what is this sigma 1/2? Sigma 1/2 is really half of this eigen decomposition. Now, if I have this sigma, I run an eigen decomposition, I will be able to obtain this u lambda and u transpose. Okay, the eigen decomposition was discussed in the previous lecture, and this is the decomposition for sigma. And now, if I add a half over here, then this thing would become my sigma of 1/2. This is how I defined my sigma half. Sigma half is defined as this term. So instead of using the full lambda, I'm using half of the lambda. And remember that this lambda, this diagonal matrix, is always non-negative, and so taking the square root is not a problem. Okay, so what is the product? Well, this product is still a square matrix. It has the same size as the sigma. It's just that the all the eigenvalues they have taken a square root. So you have this, and then you multiply your x each data point with the sigma half plus mu. You'll be able to get a y. Y will be this Gaussian in with mean mu and variance sigma. So this is really the step as I'm drawing here. Take a data point, do the transformation for every data point, then you can transform this data set into a new data set. This data set is Gaussian 0, 1, and then this data set will be a Gaussian of mu and sigma. So that is the transformation that you want to do. So here is a pictorial illustration of what is going on. Originally, you have this Gaussian random vector. Let's say you are looking at a two-dimensional space. Then it has to be a circle. This covariance matrix is identity, and therefore you have a circle. And then you do this transformation. What you will get is that the center will go from the origin to this new center, which is here. And in addition, this circle will change its orientation and also the size. It will become an ellipse. The radius of this ellipse is determined by the eigen decomposition of sigma. So you have this lambda 1, and then you have this lambda 2. This direction is u1, this direction is u2, something that we discussed last time. So this is the transformation that you're applying to turn x into y. So let me just quickly go over the proof. The proof is pretty informative in telling us why this is the case. So we take this transformation. This is the transformation that we propose. So here is y equals to sigma half times x plus mu. And then I want to show what? Well, I want to show that the new mean and then the new variance will correspondingly become expectation of y. Okay, so the new mean will become mu, and then the sigma y, which is the covariance matrix of y, will become sigma. Now, note that if you take the expectation of x, that is 0, and then if you take the sigma of x, that is identity, right? So this is what we start, and then we want to go to here. So how do we prove? So let's look at the mean. The mean, the expectation of y, is really the expectation of this term. Okay, and then now you look at this. This is the expectation on a matrix times a random vector. Expectation is linear, and therefore expectation, when it applies to all these summations, this matrix vector multiplications, the expectation will go in. So when the expectations go in, you can pull the sigma half outside, and then you have this expectation of x. The expectation of mu is just mu. Mu is a deterministic vector, so it will come out. And then what? And then you ask, what is the expectation of x? Well, because expectation of x is 0, this is how we define the problem. So this would be gone. And so you have 0 here, and then that would disappear, and therefore you will have this mu. Okay, so you have this mu. Mu is the mean of this random variable y. Okay, so we have proved that the mean of y is mu. Now, what do we want to prove next? We want to prove that the covariance matrix of y is indeed sigma. So how do we do that? Well, we define the covariance matrix. The covariance matrix of y is defined as y minus mu and y minus mu transpose. We take the expectation outside over all the possible y's. And then what? Well, then we plug in this definition here. So this is the definition of your y. This is your definition of your y, and then you have a transpose. And then we do this multiplication. Okay. Now note that there is a mu and then there's a minus mu. This minus mu comes from your definition. So that is your minus mu. And then this plus mu comes from the definition of your y. And therefore you can see that there is a mu here, there's a mu here, they will cancel out each other. That will give you this sigma 1/2 and then x, sigma 1/2 x, and then there's a transpose outside. Okay, so when you have this transpose, then you can rearrange the terms. So here you will have expectation of sigma 1/2, and then you have x and x transpose and sigma 1/2. Remember that the transpose, when you apply to a product matrices, the order of the transpose will change. So when you have this, then you know that the expectation can go inside to this thing, because sigma half, they are deterministic matrices. So you have this expression. You have sigma half expectation of x transpose and sigma half. Then we ask, what is the expectation inside? This expectation is identity. Because why? Well, because here, this is how you define the covariance of x. This is the expectation of x minus mu x times x minus mu x transpose. And what is mu x? Mu x is 0 because of this definition here. So they're gone, and therefore you have expectation of x transpose equals to identity. That's why you have identity here. And the identity doesn't really matter when it goes to this product. So you have sigma 1/2 times sigma 1/2, that will give you sigma. Therefore, when you take this covariance matrix of y, you will obtain sigma. And that concludes the theorem. The theorem says that you start with a random vector x, which is 0 mean unique variance. You take this transformation, you'll be able to get a new random vector y, which is distributed according to mean mu and then variance sigma. So that is the transformation. This is a diagram showing you how we actually do things, and I hope that from the previous lectures you should have learned how to do this visualization on a computer. Now, if you're interested in the detailed commands, you can go to the ebook and then you can see the exact numerical values that I used to generate this example. Now, here, this is a distribution for x. It is a circular. It has a circular covariance matrix, meaning that it is Gaussian with mean 0 and a variance of 1. So this is the original input. And then you take this transformation where you say y equals to sigma 1/2 of x plus mean mu, then this is your new distribution. In this new distribution, you can see that the center is moved to here, and then the orientation is also changed. All right, so this is the first half of today's lecture. We talk about how we transform from zero mean unit variance to the arbitrary mean and arbitrary covariance. Now, the reverse direction is called the whitening. Whitening of a Gaussian. So you ask, what is the equation? Now, if I tell you that y equals to sigma inverse of x plus mu, I ask, what is the inversion? Well, the inversion will of course be y minus mu, all right? And so you pull the mu to the left-hand side, that will give you sigma x, and then assuming that the covariance matrix is invertible, then you should have this being your inversion. And this is indeed the case. If we set x equals to this equation, then you can show that x is distributed according to Gaussian of zero mean and unit variance. So the procedure on a computer is also quite straightforward. You have all these data points. These are your y's. You just take this transformation for every data point individually. So you follow this equation here. This is the equation that you apply. Just the step that you do here. You go to a new data set. This data set will be a set of x, and then they are zero mean and unit variance Gaussian. The idea here is the following. You start with an arbitrary Gaussian. You have a mean here. You have a covariance matrix given by these. If you take this inversion, what's happening is that you first subtract the mean. Okay, so you first subtract the mean, and then you rescale whatever radius that you have imposed onto this y matrix. Then you will get back to this x. So this is really going backward in the direction to find out the zero mean unit variance. The proof here is almost identical to the previous proof. And I will just quickly walk through this with you. So you start with a y. This is your proposed transformation. You want to show that expectation of x is 0. Is it the case? Well, let's plug in your proposal, which is sigma half, and then y minus mu. Sigma has nothing to do with your y, so the sigma will come out, and then you have expectation of y minus mu. Now, what is the expectation of y? Expectation of y is mu. That is how you define the problem. And so you have expectation of x that is 0, as what we have promised. The other part is to compute the covariance of x. Covariance of x is defined as this. So what is mu x? Mu x is 0 according to what we have just calculated. So you have simplified the equation to this. And then you plug in your proposal, which is a sigma inverse half, and then y minus mu, etc. Again, this expectation. has nothing to do with your sigma, so the expectation can go in. So you have this expectation of this product terms, and then you ask what is the expectation of this term. Well, the expectation of this term is sigma. This is how you define the expectation. This is sigma. So you have sigma, but then you have minus half on the two sides. They cancel out. They will give you identity, and therefore the covariance matrix of X is identity. So this completes the proof. Alright, so what have we learned in this lecture? We have learned two very, very important techniques. One is turning the random vector X into another random vector Y, where X originally is zero mean and then it has a covariance meaning identity. The new transformed variable will have a mean of mu and covariance sigma. The way to do this is to apply this equation. You have sigma half and then you have plus mu. The reverse direction is called the whitening of a Gaussian. The formula for this transformation is sigma, there's a minus, don't forget there's a minus 1/2, and then there is a ym minus mu. Okay, so this is going from X to Y, and then this is going from Y to X. So now we have completed the picture of doing the transformation of Gaussian random variables. Together with the eigen decomposition, we have a lot of powerful tools to deal with high-dimensional random vectors. So I will encourage you to really try this again, also on a computer, because implementing things on computer is the best way to understand the picture of these techniques. Now, if you have any question, I will encourage you to send me email, and please also feel free to post your questions on Piazza. I will be very happy to help you on these problems. Thank you very much.